Hey guys, we're looking at piecewise functions today, and when we do that, we can also look at intervals of increasing, decreasing, and constant, which you should have looked at last year. So a piecewise function is a function that is made up of more than one type of equation or one. So each piece of the function is made up of a different equation. So you have to be able to read domain and range to be able to do these. So let's look at the first one. We have g of x is defined by x when x is greater than 0, and it's defined by the bottom part, negative x, when x is less than or equal to 0. So let's go ahead and graph that first. What I'm going to do, draw my axes. And so at x is equal to 0, looks like that's kind of where our boundary line is. So somewhere right here. On the right side of the graph, we're going to graph the line y equals x. So we're going to graph y is equal to x. And on the left side, we're going to graph y is equal to negative x. So on the right side, I have a y-intercept of 0, and I'm going to go up 1 over 1. So I get a line that looks like this. And then on the left side, our slope is negative 1. So our line looks like this. Okay, what does this function look like? Oh yeah, this is y is equal to the absolute value of x. So, which is equal to the piecewise function negative x for x's that are less than or equal to 0, and positive x for when x is greater than 0. How come we can only have the equal sign on one part of the line, even if it's continuous? Well, on the left-hand side, where the graph is less than x, it approaches 0, and then at x equals 0, the point is defined. Technically, on the right-hand side, there's an open circle here. And we do that so that if both of these pieces had, so if both of these pieces had the equal sign in this, the function would not be a function. We'd have two x values, or two different parts where the function would be defined twice on the same x value. So that's a problem for us. Okay, so so we can have a function still. Okay, so for this graph, where is the graph decreasing? Well, it looks like we read these, the increasing, decreasing, it's like a mini domain. So what x values is the graph decreasing? It's decreasing on this arm. That arm extends out to infinity, negative infinity. So this is negative infinity to 0. And it says open interval. So I'm actually going to use an open parenthesis here. I don't have any constant intervals. And then lastly, the interval here on the right-hand side is increasing. So from what x value? From 0 all the way onward to infinity. So from 0 to infinity. Again, open intervals. Next one, we're going to go ahead and evaluate. So when you evaluate a piecewise function, you have to be careful about which part of the function you use to plug in the x value. So when x is equal to negative 3, I have to look at, okay, which of these functions has negative 3 in the domain? So I'm like, oh, x is less than or equal to negative 1. Oh, that one goes to the first one. So f of negative 3 is going to equal negative 3 squared. So f of negative 3 is equal to 9. So when I have x is equal to 1, which of these three functions has the domain, is negative 1 in its domain? Well, the top one again. So f of, because it has the equal sign, negative 1 is equal to negative 1 squared. F of negative 1 is equal to 1. All right, when x is equal to 183. So 183 is in this the third functions domain. So f of 183 is equal to 5. It's constant there. Okay. All right. We're going to write the equation of the piecewise function. So we'll call this h of x. H of x is equal to, and how many different functions am I going to have? It looks like I'm going to have 1, 2, 3, 4. 4 different pieces. So the first equation looks linear equation. I'm going to start at 1, 2, 3, 4. And my slope is positive, so plus, I'm going up 1, 2 over 3. So 2/3 x. And the domain would be from negative infinity is less than x, and that's less than, and then I'm going to look at where my domain is here at 0. So this graph stops at x equals 0. The next part is at right here. It looks like it starts at 0 and goes to 1. So the domain is going to be from 0 to 1. At 0, the point is there's a solid dot, so that's included. Are we included at 1? No, it's an open dot. And the function on this piece would just be a constant 2. Next part. I have an equation decreasing. And I am a point slope fan, so I'm going to use this point on the line, which is, the point is 2, 1, and the slope is -1. So the equation for this line would be y minus 1 is equal to -1 times x minus 2. And I'm just going to add the 1 to the other side. So -1 x minus 2 plus 1. Or you can simplify it. Simplify -x plus 2 plus 1. So y is equal to -x plus 3. Okay, so y is equal to -x plus 3. What is the domain for that function? Looks like we start at 1 and go to x equals 2. So 1 is less than x and is less than 2. Which points are included? It looks like the only point that's included is that one. Okay, I'm going to make sure if there's an open circle right here, so both of the ones are not going to have an equal sign on them. Okay, last part. Let's go. Okay, that's a constant at 1, and it starts at domain is 2 is less than x and is less than 1, 2, 3, 4. Okay, 4 is definitely not included. There is a closed circle at 2, but since we made the top function have the equal sign, we can't make the bottom one have the equal sign. It doesn't matter which one in this case because the function is continuous there. Okay, and that's it. We're done there. Lastly, we're going to graph. All right, here we go. Okay, that's pretty close. All right, so first off, I'm going to break up this. I'm going to break up this function, this graph, sorry, into its mini domains. So I can see where the first function is x is less than 2. So the first function is only going to exist on this area. The next part is that x is from 2 to 4. So right here. So this is going to be function number 2. And the last function is going to be onward from 4. Okay, so I can definitely, I'm going to start with the middle one. So f of x is equal to 6. So 1, 2, 3, 4, 5, 6. I'm going to go ahead and draw in the line. And neither of those points are included. So I'm going to, for now, put open circles. The next part, let's go back to the first graph. 3x that has a y-intercept of 0 and a slope of 3. So up 1 over 3, up 1 over 3. And we are defined at x equals 2. So this open circle is going to change to a closed circle. Okay, open circle changes to a closed circle. All right, lastly, 1/2 x plus 1, negative 1/2 x plus 1. So I am going to go ahead and graph this in fully. So I'm going to go up 1 for the y-intercept, and then we go down 1 over 2, down 1 over 2, and down 1 over 2, down 1 over 2. But I don't graph anything over beyond that's less than 4. So I am going to start from our domain boundary right here, and I'm going to go ahead and graph in this line. Is the dot open or closed at 4? Well, because there's the equal sign, we're going to be a closed circle. When x is equal to 6, that endpoint is going to stay an open circle because it is not defined in that function. Okay, so I'm going to erase all the extra parts now. That part, all of our domain boundaries that we made at the beginning. And this is what our function looks like. So the last thing we can do is just look at what sections are increasing, decreasing. Oh, I got rid of my axes. Sorry. Okay, so we're increasing from when x is 0 to x is 2. So from 0 to 2. And again, it says open intervals. Okay, we're constant from 2 to 4. So 2 to 4. And decreasing from 4 to infinity. And that is it for today.